thank a higher DOT for allowing me to do this remotely. That TRB lurgy got me, and it would have been really tough to get on an airplane yesterday. So thank you for setting up the technology, and hopefully we can still have some fun, present some good data and some answers. This is a final wrap-up report for a research project we have been running for you over the last 2 years. It's been a partnership between Iowa State and Ohio University. And the brief that we had was to see if we could find a way to improve bridge deck life by looking at the mixture construction systems and that sort of thing. So the goal was improve asset management by reducing the need to replace bridge decks as often as we have to. You know, there are a lot of pretty old decks, and in some ways the inspiration is the old covered decks, covered bridges, where the primary reason for putting the cover on was to protect the bridge deck. Now I think we can do a little bit better with our bridge decks and make them able to survive the environment, and so remove the need for the cover. Part of the brief was to look at internal curing, or if there were any other high-performance technologies that could be used to improve life of these decks. So the first question we had to ask ourselves was, what is success? How do we know that we're doing a good job? Now, the things that primarily go wrong with decks is they crack, and the cracking is caused by a differential drying. We want to control the strength, and we want to also influence the modulus of elasticity, and I'll get into that a little bit later. The other thing for northern states like ours, we want to be able to resist the cold weather. So again, impermeability, the ability to keep those nasty de-icing salts out of the deck, is fairly critical. Now, again, I call them nasty as a driver with relatively young driving children. I'm all for lots and lots of de-icing salts because it means I don't have to replace their cars quite so often. But from a concrete technology point of view, these de-icing salts do have an effect on the concrete, and we need to compensate for that as we design our systems. Impermeability, and the other one is providing a rigorous air void system to reduce the risk of freeze-thaw damage. The other one is, most of the de-icing salts we use contain chlorides. Therefore, we want to protect the reinforcing steel from attack by those de-icing salts. So again, impermeability would be a very good thing. The other one that we looked at or thought about was the idea of polishing. Is a hard coarse aggregate or a hard fine aggregate would help resist that issue. It's not one we focused on under this project because in many ways the aggregate you have available is what you have available. But being aware of the fact that a siliceous material somewhere in the system would be a good thing to have. All right, the contract was set up with a number of tasks. The first was a literature review to look at internal curing, shrinkage-reducing admixtures, what other people have been doing with respect to making long-lasting bridge decks. I have to acknowledge a lot of good work done by Dave Darwin out of Kansas, and that was the basis of a lot of our thought. We also had a look at other states that have been changing the way they're looking at their bridge decks. In particular, New York has been leading the way with internal curing. We've built a couple of bridge decks with internal curing here in Iowa. In Indiana, Kansas have all been pretty active in this world. So we were able to look at what they're doing and learning some facts from them. We then developed a lab program. The basic idea being to run the tests to identify what makes a mixture good. So we were looking at the hydration rates, setting time, strength development, modulus, cracking risk, and then the permeability type measures being resistivity. And implicit behind all of this, we were also looking at the cost benefit. It's all very well to make a perfect deck, but if you can't afford to pay for it, we're no better off. We developed a trial specification, and then that specification was part of a contract that was let to build a bridge deck in Ohio with a control mixture and with the mixture that we recommended based on the lab program. Then we basically waited a year. The decks were built in August 17, and we returned there in August 18 to have a look at, well, how were these bridge decks performing? Again, helped to write some specification language, and we have written up a final report. And based on what I'm hearing back, we will put in some modifications and clarifications on that, including what we hear from today's presentation, any feedback I have from you. And then the contract will be over in a couple of weeks. I must say it's been a fun project. I've enjoyed working on it, and I think the team has as well. So what are the critical properties that we're looking for? As a good engineer, I cannot sleep at night unless I know what the strength is. The fundamental behind this, though, is to realize what controls strength. And the basis is water-cement ratio. It's all about the mixture proportioning. Yes, curing has an effect. Yes, aggregate hardness can have a small effect. Yes, supplementary cementing material dosage can have an effect. But behind all of these, the root parameter we have to control is the water-cement ratio. And basically, the lower the water-cement ratio, the better the strength is going to be. On the other hand, we're also interested in that shrinkage and cracking issue. And so, and in particular, differential drying is that if a system is wet and cool at the bottom and hot and dry at the top, you'll end up with a differential across the thickness of the section, and so invite some fairly nasty cracking to occur. Ways that we can address this is, again, the internal curing, and I'll show you how this works a little bit later. Shrinkage-reducing admixtures just reduce the shrinkage overall, and also workmanship, in which I include conventional curing, finishing, those sort of activities. The fundamentals that control permeability, again, water-cement ratio, supplementary cementing materials, and curing. And again, I'll talk about all of these in a little bit more detail in the following slides. And again, we don't lose contact with the idea of that cost is fairly important. So again, just beating this thing to a little bit harder. Water-cement ratio controls strength and permeability. The bad news is that it has a negative effect on shrinkage. As the lower the water-cement ratio, particularly if you get below about 0.4, you can end up with autogenous shrinkage. And so the risk of cracking goes up if you drop your water-cement ratio too low. The literature recommends for bridge decks a maximum water-cement ratio of about 0.5. I would also put that in as a pretty good minimum. I'd hesitate to go much above that. So let's settle on 0.45 as a fairly good water-cement ratio for our specifications. Our supplementary cementing materials will influence strength, the rate of strength gain, and impermeability. Depending on the product that you're using, and in your area, slag is the preferred and available material. In the range of 35 to 50% seems to be a pretty good number for that material. Again, balancing that shrinkage, rate of strength gain, and getting the good permeability that we're looking for. Another one that people don't think about an awful lot, but I'm trying to change that, is to look at how much paste there is. The mixture of cement, cementitious material, and water. The more there is of that in the system, the higher the shrinkage is going to be, because it is the paste that shrinks when it dries. And so we want to try and limit that number. And the way we can do that is by paying close attention to the aggregate gradation. It strongly affects workability as well. And so we're playing a juggling game of getting enough workability for the contractor to be able to place the concrete, at the same time not putting in too much paste, because that is generally negative. Increases cost, increases heat of hydration increases shrinkage. And so we come to the aggregate gradation, is that if we have a system that is well graded, then we can get better workability and yet at the same time control the amount of paste that we need. For pavements, we are recommending staying inside what is called the tarantula curve, and that envelope is shown on the bottom right-hand side of the slide. There you're getting the sweet spot between good workability and at the same time as much aggregate in the system as we can possibly get. And both of those are good things. All right, the next thing we were looking at is the idea of shrinkage-reducing admixtures. These are chemicals that change the surface tension of pore solution. And this is important because when a pore, a capillary pore is drying out, it has a fairly tight angle of surface tension, and so the force will tend to close the pore down, and that's what's basically fundamentally driving the shrinkage within the system. And so if the pore is full of water, it's pretty big, but if it's dry, it's pretty small, and hence we have the shrinkage. By changing the angle of contact between the solution and the pores, you can actually change the amount of shrinkage that occurs. These things have been in use for several years. They are demonstrated to work pretty effectively, and we included them in a couple of our mixtures just to see how they would work out. All right, let's go into the fundamentals of curing. Curing is the act of ensuring that the concrete is kept wet and kept warm during the early hydration process. Hydration is the chemical reaction between water and cement, and so we have to keep providing that water or ensure that it doesn't escape the system if we're going to encourage the reaction to proceed. We also want to keep it warm. If it gets too cold, the reaction will slow down. If it gets too hot, some interesting things may happen. So, the basic rule about curing is keep it wet, keep it warm for as long as you need. And typically for the sort of mixtures we're dealing here, we're probably looking at 3 to 7 days of protecting the concrete from the environment. Start early. It seems to be kind of pointless that if something is allowed to dry out and then you come along a little bit later and spray curing compound onto it, you're actually sealing in the dryness that's already occurred. So whatever you do with curing, start early and stay late. Internal curing is an interesting concept. Traditional curing is what we're trying to do is either seal it up on the top surface or adding additional water on the top surface. And in some ways, this may set up a differential because the external water is only coming in at the top. And as you can see in the image, it only reaches in an inch or two. And so you could have a fairly wet environment on the top and possibly a drier environment on the bottom. Again, setting up a differential that's not entirely desirable. Internal curing, on the other hand, is where we basically trap little spheres of something that contains the water. And then as the water is allowed to escape back into the mixture, you can see that the blue area where the curing has been beneficial is now pretty uniformly distributed through the whole thickness of the specimen. It's a whole lot more blue than in the top image, top right-hand image. And so we're getting rid of the differential. We're also encouraging curing throughout the specimen, and so, also in this case, throughout the bridge deck. So we're getting improved performance throughout the system. And so, theoretically, it sounds like a really good idea. And the literature, there's been a lot of work carried out on this over the last few years. Jason Weiss has done a lot of work. Dale Bence from NIST has also reported a lot of benefits. And I'm not going to go into too much detail, but in general, it's less shrinkage, which we want, reduced cracking, which we want, reduced curling, which we want. better hydration, better reaction of supplementary cementing materials, which is also a good thing because it means that we could actually insert more supplementaries into the system and again buy better performance at the end of the day. Improved durability means we can also possibly leave out some of the cement and so improve our carbon footprint and reduce the costs. And so at the end of the day, we get longer life decks. And so from a maintenance point of view, if you were to come in and replace this thing after 40 years instead of 20 as a DOT, that's a good thing. That's true. The traffic issues, the life cycle sustainability issues, the cost issues are all significantly improved. So how do we do this? I talked magically about trapping little bubbles of water inside the concrete. Now the one catch with this is that we don't want to just add water to the mix, because then you're changing the water cement ratio at the time of mixing, and that's a big fat negative. The way we do it in the US is to use lightweight fine aggregates. So fundamentally, the material should hold enough water. That's pretty obvious. It should hold the water until it's needed without affecting the water cement ratio. It should give up the water when we want it and not have any other negative effects on the quality of the concrete. And a dosage of lightweight fine aggregate seems to hit all of these buttons. It's providing us with a tool to get the water where we want it and make it available for curing when we want it. Some of the work by NIST and some of the exotic chemistry and number crunching and modeling basically comes down to a pretty simple answer. We need about 7 pounds of internally provided internal curing water for every 100 pounds of cementitious materials in the mixture. And so it's a pretty simple spreadsheet, and I can send this to anybody who needs it. Otherwise, Jason Weiss has a spreadsheet, and the Expanded Shale and Clay Institute has a spreadsheet. But basically, if you know the properties of the aggregate that you have, so if you look at the bottom right hand, there it is, there's my mouse, is if we know the absorption and desorption of the lightweight fine aggregate that we're providing, it's a pretty simple calculation that comes back and says you need about, in this case, 230 pounds of lightweight fine material to replace the conventional fine aggregate. That's enough. That's what we need to get a rigorous set of internal curing. So the quantities are not great. The other point to make here is the fine aggregate is preferred rather than coarse aggregate for much the same reason that we want small air bubbles, is that we want each fine aggregate particle has a radius around it that influences the paste in contact with it. And so the smaller and greater number of these particles we have, the higher probability we have of providing that benefit to the whole paste system instead of a few isolated spots. So we go with a fine aggregate, and again, the properties, how much we need does depend on the properties of the aggregate that we have, but it's a pretty simple calculation to do it. So we need the one negative of this is we need an extra bin, and we have to ensure that the aggregate going into the batch plant is pretty close to saturation and yet not too wet. And the way New York DOT set it up, their specification states the sprinkler should run from the aggregate should be run under a sprinkler for about 48 hours, and then you allow it to drain for 12 to 15 hours. Now, we had occasion last year in Iowa where we were doing this, and that it was raining solidly. And in the end, the decision was that the draining was less critical. We could back calculate how much water was coming in with the aggregate on the surface, and so we could still control the water cement ratio of the final mixture. But it is a good idea for the aggregate to be thoroughly wetted. Now, we're not talking about huge quantities. If you look at a typical bridge deck like the one we built, I believe we're only looking at a couple of truckloads. So it is a pain, but it is eminently manageable. Now, when we come to pavements, it's a little bit harder because the quantities go up pretty quickly. Does it mean we can do away with conventional curing? And the answer is preferably not. Is that the internal curing will reduce the rate of drying at the top surface, but on the other hand, it doesn't stop it. So from my point of view, it is still a good idea to keep the surface from drying out prematurely. We need to have either a burlap, a flooding, and or a sprayed curing compound system to get belts and braces to get everything running properly. All right, so we ran a fairly rigorous program through the lab. We played with Portland cement that we obtained from Ohio and a slag cement from Ohio. We contacted a silica fume supplier. The thought being is that if we put a little bit of silica fume into the mixture, we would significantly decrease the permeability of the system, and we wanted to see if we could still get crack-free environments with that. We used Iowa limestone aggregates just to keep the costs of hauling material down, but they were not very different from the materials that you have locally in Cleveland. We also obtained samples of 2 lightweight fine aggregates from 2 different manufacturers, again from Ohio. So we were using the critical materials that are available in your area. Admixtures, we obtained locally available chemical admixtures as air entrainers and high-range water reducers. We measured the specific gravities of all of the materials, and you'll see that the lightweight materials are considerably lighter than the conventional materials and also have considerably higher moisture absorption. And that's exactly what we want. I think the specification that we've published recently, we're asking for absorptions greater than 15%. So we put together a test matrix where we did 30% slag, which is pretty much your standard approach. I also decided to push the envelope up to 50% slag and see how well it would perform. We also ran with a 30% slag with 4% silica fume. Our aggregate systems were typical aggregate gradations, or your typical aggregates, or substitution with about 25% by mass of either of the lightweight fine aggregate materials. We also ran a couple of mixtures with and without shrinkage reducing admixtures to see what effects they would have. The mixed proportions, we took the approach we're using in the PEM program is first looked at the aggregate gradation. So we optimized the gradation for the materials that we had in order to stay inside the tarantula curve, and we managed to do that. We also limited the paste quantity by limiting the total cementitious material to functionally a 6-sack mix. We may have been able to pull it down a little further, but we settled on a 6-sack mix, as that is fairly typical of what happens out there. And again, this is based on guidance from the literature that we don't want to have too much paste in the mixture. Here are the plots of the gradations. It's not a lot of information in this chart. But the real interesting one is this tarantula curve at the bottom, is that we ended up with a pretty good gradation at the end of the day. What is interesting is both the lightweight fine materials are these two. A little bit coarser than the fine aggregate, but they help to straddle the gap between the coarse and the fine material. So they actually provide us with a slightly better gradation at the end of the day. Now, I'm not going to chew on this one a whole lot, just to say we produced 11 mixtures with different dosages of slag, SRAs, and the 2 different lightweight fine materials that we played with. The properties that we measured, the fresh properties, slump, of course, the unit weight and the air content. We measured setting time using calorimetric approaches and conventional pin-based devices. The Hardened properties, we looked at strength, modulus of elasticity, shrinkage, both the free test and the shrinkage ring. We also measured resistivity as an approach of assessing the permeability. So again, the better the resistivity, the longer the system is going to last. We also did a little bit of work looking at abrasion resistance. All right, here's the table of the data, and it's a little bit too noisy, but I've got some graphs coming up that'll help identify it. But basically, we were running in a 3 to 4 inch range slump. Our air content was 5 to 8%, which is fairly typical of bridge deck specs. Time of set generally was in the 3 to 4 hour for initial set. Where we did see a little bit of a jump was one of the SRAs kicked it up fairly high, but otherwise we were all pretty consistent across the mixtures. The unit weight, the interesting thing about this is that the conventional mixes up here on the top right were typically about 145 pounds per cubic feet. The mixtures containing internal curing, or the lightweight fine aggregate, were about 5 to 10 pounds lighter. And that's not a bad thing. It's not a big change, but it's not a bad thing from the point of view of loading on the bridge deck at the end of the day. All right, so the setting time where there is a fairly big signal is the 30% slag, typically set at 3 hours. The 50% systems were quite a lot slower. The silica fume brought it back down a little, and the SRAs also slowed things down fairly significantly. But in a way, there's no right or wrong answer on this. It just needs to be communicated to the contractor that, things are going to be slowed down. The way they do finishing and curing have to be adjusted a little bit. Is that we don't want to put curing compound on too early. We also don't want to be doing final finishing too early if the system hasn't set yet. Again, a table full of the Hardened properties. Again, the flexural strengths are all pretty similar. Compressive strengths were all well above 6,000 psi, or pretty close to 6,000 psi at 28 days. The one that I did want to flag here was the modulus of elasticity was notably lower for the systems containing the lightweight fine aggregate here on the middle right-hand side of the chart. And in this case, a lower modulus of elasticity is a good thing, because for a given strain, if you have a lower modulus, then the stress is reduced, and so your cracking risk is reduced. All right, moving on to the resistivity. This is a relatively new approach to assessing the potential durability of a mixture. Resistivity is a measure of how easy it is to conduct electricity through a sample. Now, rock and sand are not very conductive or have a high resistivity. Cement paste does have a slightly higher resistivity, and water or any porous solution, paste has a lower resistivity. Porous solution has a very low resistivity. And so you can see that if we have a system with a high resistivity, it means that it's going to be a lot harder for the water to get through. It's a bit of an indirect measure, but if there is a higher resistivity, there is less fluid in the system, and that's a good thing. That's fundamentally what we're trying to do. So the chart, again, lots and lots of data, but what it's showing us is that the three systems of 30% slag have an acceptable, but still relatively low resistivity. High is good, low is less good. Now, typically, other states are saying you want to be around or above 28. And so we got pretty close to that with all of these mixtures. But you can see the systems with internal curing with the higher slag content all did far better. And so that was a fairly loud signal. The one that did best of all had lots of silica fume in it too, but there were some negatives associated with that mixture, which I'll come to a little bit later. Now, from a structural design point of view, we just compared the ACI 318 model for the three different aggregate systems, and the conventional aggregate system ran parallel to the model. The two lightweight systems did not. So again, it may have to come back to the bridge designers, when you're looking at some of the other aspects of thickness design and cracking risk, is that the 318 model doesn't work for these materials. We need to recalibrate how we apply that term into any modeling that we do. All right, this is the fun one. Shrinkage. This is from the drying shrinkage ring test. For those who don't know it, it consists of a steel ring, basically a steel pipe, 12 inches in diameter with a very thick wall, and it's about 3 inches high. And on the outside of it, we cast a donut of concrete. The ring is instrumented with strain gauges, and you can understand that as the concrete dries, it will grip itself around that ring, and so you end up with a compressive stress inside the steel. And the higher the stress, the compressive stress in the steel, the higher the tensile stress in the concrete, and so the higher the risk of cracking. And you can see pretty clearly here is that the two systems containing, the three systems containing silica fume, the black dotted lines, had relatively high shrinkage. All of the others did quite a lot better. A couple of them did crack out. But the best ones, again, seem to be the ones with the shrinkage reducing admixtures. The 50% slag mixtures are the green ones, and the 30% slag mixtures are the red ones. So again, we're balancing our desirability here. Is again, the lower the shrinkage, the higher up we are on this chart, the better off we're going to be. And basically what we're doing is a trade-off game of what's good enough. There is no perfect answer. Sorry, I'm being stupid. Comes with having a cold. These are the drying shrinkage, the C157 prism tests. These are the data from the rings, and you can see that several of them did indeed crack. The ones that jump up is where the system cracks, and you get a sudden drop in the stress. But again, very similar results is that the slag systems do better, the lightweight internally cured systems do better, and the shrinkage reducing admixture systems do very well. So we've had a whole lot of data, and it became an interesting conversation about, well, how do we know which is the right one to choose? And the approach we took is an approach we've used in other research projects, is to take each of the critical parameters and to choose, in some cases, an arbitrary pass-fail number, and in some cases we chose a fairly rigorous number just to make sure that something failed somewhere along the line. So, temperature rise, we used the calorimetry approach. We measured the change in temperature over time and assessed which is the one systems that got hottest fastest. And in many ways, the idea being is that the higher the temperature rise, the higher the temperature differential, the higher the potential stress in the system. So we imposed, again, an arbitrary 20-degree maximum rise. On the splitting tensile, most specifications run with a 600 or 650 psi minimum. We chose the 600. Compressive strength, we went to the 5,000 psi minimum. Modulus of elasticity, we went to the 5,000 ksi maximum. For resistivity, we chose that number I referred to, 28 kiloohm centimeters, as a minimum. Free shrinkage, we went to 300, which is the number I've seen in several specifications. And then from the ring shrinkage test, there are two parameters that we looked at, is the rate of stress development and a parameter that you can extract out of the data with a risk of cracking. And so all of the cells with a blue shading are cells that seem to do better. Now, again, 4,000 psi is probably more than you need. In fact, 5,000 probably way more than you need. But I was trying to filter out the systems that did better. And by basically coloring in all the cells that pass these somewhat arbitrary but reasonable pass-fail parameters, we basically whittled it down to two different systems that seem to provide the best bang for the buck. Now, again, any one of these would probably be acceptable, but I was going for an optimum. And in these cases, the two that worked really well were the systems with 50% slag, no silica fume, and with internal curing. Now, the shrinkage-reducing admixtures, again, did really well in the shrinkage parameters, but they did hammer the setting time and the strength development. Silica fume systems did really well from a permeability point of view, but did not do so well from a shrinkage point of view. So based on that, we seem to have settled out on a system that we could move forward and recommend to the DOT is a 50% slag, lightweight fine aggregate system would seem to provide a really good way to go. And so we had a few discussions with the DOT staff and worked with them to set up a specification for a bridge deck, one with and one without the internal curing. And again, we measured the properties of the concrete mixtures. Right, the two decks were on Route 271 in Mayfield, pretty close to where you all are right now. The control deck was placed on August the 1st, 2017. The test deck was placed 10 days later. The mixed proportions that we settled on were the control deck was pretty much your standard mixture. It was a 30% slag mixture, water cement ratio 0.45. The internally cured deck, we went with a 50% slag, and again, a small amount of lightweight fine aggregate. And you can see here, it's not a huge amount. Of the 1,300 pounds of fine aggregate, we're only replacing about 200 of it with a lightweight material. So the quantities are not huge. The coarse aggregate didn't change an awful lot. And as I said, we ran with a water cement ratio of 0.45 to be the sweet spot between, if it's too high, we don't get mechanical performance. If it's too low, the shrinkage risk seems to go up fairly quickly. So again, thanks to some help and support from University of Ohio, who sent a team out, we measured the unit weight, and again, the control mix was about 3 to 5 pounds heavier than the internally cured system, and that's to be expected. The air content was pretty close. The slump was in the 5 to 6 inch range. Now, I believe I heard this from this construction site. I've certainly heard it from other sites in Iowa where the construction crew has been told, the reason there's a whole bunch of university types lurking around and poking around and sticking stuff inside your bridge decks and getting in the way is because you're working with a fancy concrete. What did happen, certainly on the one deck we were working on in Iowa, is we cast the the east side of the bridge with the internal curing and the west side of the bridge with the conventional mix. And when they put the internal curing section down first, and then without telling anyone, just changed the mix back to the conventional mix and kept going. And about halfway through the second half, the conventional mix, one of the finishers on the deck wandered up to one of my staff and said, okay, so when do we get to play with this fancy concrete? And it was actually kind of pleasing to be able to point to the stuff they'd already finished and said, that's it. And they hadn't noticed. So, the effect on the constructability is invisible. Again, the issues are more on the stockpiling and preparation, but the constructability itself has zero effect. The curing was based on the higher specification, wet curing placed immediately after finishing using burlap. That was stripped off after 7 days, and a curing compound was applied. And that's not a bad way to go. So again, samples were taken from the mixture as it was delivered and tested in the lab. And what's interesting in this case is that the compressive and the tensile strengths were markedly higher with the internal curing, particularly at 28 days. And again, this is partially due to the increased slag content and due to the fact that the internal curing is indeed helping the hydration along. Now, again, for a system that's under standard curing, one would question whether or not the internal curing is making a whole lot of difference. And that's, we do in the lab work, we do see some benefit. And I think it's all to do with, again, the uniformity of the curing provided to the whole system. We also buried thermocouples into the concrete, and what it's basically telling us is the dotted lines here are the environmental temperature, so the daily up and down. The control concrete did get pretty hot. The internally cured concrete did not go through that same spike, and again, I think that's largely a function of the higher slag content. But what's interesting is that over time, the internally curing kept going. So the heat of hydration kept the concrete a little bit warmer than the conventionally cured system. And that's exactly what we were looking for. It prevents the spike, but at the same time, it keeps the hydration going. And more hydration is good. Anytime, it's a bit like the three fundamentals of buying property. It's location, location, and location. As a concrete geek, the properties of the concrete are controlled by hydration, hydration, hydration. And here we can see very solid evidence that we were getting far better hydration than the control system. And that's a good thing. It's giving us the strength. It's giving us the impermeability. It's encouraging the system to get up there before we expose it to the environment. Okay, here's a photo of the resistivity device. It's basically just a little 4-pin probe. You hold it on the side of a wet cylinder and push a button, and it spits out a number which is kiloohm centimeters. And again, the joy of this test is that you can test the same sample. It's non-destructive. So having done the test, you can put the sample back in under curing, come back a few days later, and do it again. And here we see a real significant difference, is that the internal curing concrete has really climbed while the conventional mixture flatlined off. Now, these numbers are not quite so pretty, and again, I would attribute this excellent performance both to the internal curing and the higher slag content. All right, we also measured shrinkage. Samples were taken using the prison test, run back to Ohio University's lab. And again, what we're seeing pretty clearly, the internal curing had a slightly lower free shrinkage, and that's altogether a good thing because shrinkage is related to cracking. All right. I'm sorry. All right. We also buried strain gauges and thermocouples in the bridge deck itself, so we could track how these things were running. And so this is the internal curing bridge deck, this is the conventional deck, and there was all sorts of wonderful devices placed inside the concrete. And if you have any questions about this, Eric is on the line from University of Ohio. He can help catch some of the questions a little bit later. But basically, what we were seeing is that slightly less variability in movement between the conventional concrete and the internally cured concrete. So again, expected diurnal temperature-related movements and much less differences top to bottom between the top and the bottom of the deck. So again, not a huge change, but the change that there is for the good. We also put strain gauges underneath the bridge decks, and we did a load test. Drove a truck over the deck a week or two after the deck had been constructed. We did it in 5 different locations and measured the differential movements. And again, if you want the full details, go chew on the report, but there's not a lot of difference here. It is that structurally, these two decks are performing very, very similar to each other. So, from a point of view of deflections, movements, strength, all of that good stability, all of that good stuff is the same. And again, that's a good thing. Again, for the structural point of view, having no change is to be desirable. We also came back a year later, and we did we didn't do load tests after a year. We have done load tests on other decks after a year, and again, it points to very little difference. There's as much the variability between these systems is as much due to noise in the system as anything else. So no consistent difference in structural response between the two decks. All right, we did put a free shrinkage prism next to the deck just to see how that would compare. And again, the gray line here is the free shrinkage prism. The orange line is the strain gauge in the deck, and the blue line is internal curing near the top of the deck. And again, you can see that the strains are generally lower in the internal curing, and even lower than in the free shrinkage sample. And that's to be expected. Is that relationship between free shrinkage and actual shrinkage in a structural system is a little tenuous because we've packed the thing full of reinforcing steel. Again, fairly consistent and desirable behavior out of this thing. This is where it gets to be really exciting. We went back a year later and we counted cracks. And you can see from the top image, the conventional deck had a fairly typical distribution of cracking, mostly near the middle of the panels, and nothing too crazy, but quite a lot of cracking. Then you come down to the internally cured deck, and there's two very small cracks. That's it. So, I got a phone call about this late on a Friday night when the crew were on their way home, and my wife was kind of freaked out about why I was jumping around the living room. That this is really exciting. That we've managed to build a bridge deck that didn't crack in the first year, and that was the initial charge out of this project, and it's fantastic to be able to say, yeah, I think we did it. We delivered without significant impacts on constructability. And even with the increased slag content, from what I can gather, the scaling has not been excessive. By paying attention to curing and finishing, we've got a really good deck running here. It's certainly the way to move forward into the future. So, have we succeeded? Yes, we believe we had. We didn't pay a lot of attention to the polishing, but we managed to check the boxes on everything else. So, yeah, we did it. Again, I talked a lot at the beginning about life cycle costing. There is a premium. This lightweight fine aggregate is not free. Now, there were two sources in or near Ohio. I've heard rumor this week that one of them is shut down. But I know that from Iowa that the cost of delivering the material is about $3 a yard premium over the regular aggregate. Now, in this case, there was a cost associated with the handling and installation and processing and preconditioning of the aggregate. So there is certainly a contracting cost on dealing with this stuff. And so we did a life cycle cost assessment. And what we found is that based on the data we've collected, the permeability data, is that the initiation to corrosion of the reinforcing steel, this was done using Life 365, is we more than doubled, if not trebled, the time it took, the time it will take for corrosion to initiate on the reinforcing steel. The propagation has been slowed a little bit, but if it means we can buy an extra 40 years out of the system. That's not trivial. So even with a fairly significant handling and premium delivery cost, the initial repair cost on a total bridge, the the premium compared to the total cost of the bridge was relatively small. And when you compare that to the costs of maintaining the system over a 20, 30, 40, 50 year cycle, it's pretty small. And so we still believe that from a life cycle point of view, the system is eminently beneficial. And so, lab mixtures provided aggregates, adequate strength, shrinkage, and crusting risk. There was no difference in structural performance between the two bridges. We have shown significantly less cracking after 1 year, and life cycle assessment seemed to indicate that we're still better off by taking this approach. So my recommendations moving forward: bridge decks should have a water cement ratio of about 0.45. I'm reluctant to go any higher because your permeability will be compromised. From a bridge deck, it's probably not a good idea to go too much lower because of changing the cracking risk. This number is pretty consistent with the literature. Slag cement seems to buy us a lot of properties. The reduced or the improved permeability, the improved strength, partially due to the lightweight fine aggregate, partially because of the presence of the slag. I would recommend the practice of using internal curing, either using lightweight fine aggregate. There is some work starting off in this country. The Europeans like the idea of using superabsorbent polymers, basically the stuff that goes into diapers. You can put that in. It has a similar effect. Not many people have played with it in this country, but there may be something worth looking at in the future. Consider SRAs. They will help you with the shrinkage. They do have some other negative side effects. The other thing is that they are reasonably expensive, so we have to rework the life cycle benefit of those products. Control the paste content with a good aggregate gradation. I cannot emphasize that enough. It's all very well to control water cement ratio, but again, shrinkage is primarily controlled by the paste content of the mixture. Therefore, minimizing that would be a good thing. And again, guidance is available. We can help any of the contractors with meeting that with the materials that you have available. So that to me is the guts of any specification that we want to prepare. And we provided a model document that we poached fairly liberally from New York. Just out of interest, New York State has now guidelines very similar to this is their standard default position for any bridge deck that they build from here on out. Internal curing, theoretically sound. From a concrete materials geek, as a lab guy, it's fantastic. It's a good thing. From a contracting point of view, I fully acknowledge the stockpiling and handling challenges, is that you do have to provide an extra bin. You have to provide drainage. You have to provide sprinkling to make sure that that material is saturated surface dry when it's going into the batch plant. I would counter that, again, with a bridge deck, you're not looking at a huge amount of material. The contractors that we've worked with have grumbled, but have done it pretty successfully without too much difficulty. Again, for a pavement, those difficulties escalate very quickly, but from a bridge deck, it's eminently doable. There's very little change in the structural performance. So your structures guys can all go back to doing what they do. You may want to revisit your modulus of elasticity model, but what we've seen in the decks we've built, you can't tell from the load deflection, strain gauges stuff that there is any noticeable difference. And there is a huge benefit from durability and the cracking risk. So the challenges, the availability of lightweight fine aggregate. This is a map extracted from the SCSI Association website that, there is one plant, or as I say, I heard rumor that one plant had shut down, but there was a plant in Cleveland, a couple, one in Indiana, one in Kentucky, and a couple in New York. So the distances aren't huge. It's certainly quite feasible to haul in a couple of truckloads and get them to any construction site in Ohio. As I said, stockpiling and preparation is an issue, and we have to face that head on, and there's no getting around that. The other biggest challenge, perhaps, is the fear of the unknown. That every time I've worked with the contractor, there's been quite a lot of fear, quite a lot of, this is going to ruin us, my life is going to be miserable. But you know, as I said, once we get to the actual construction, the finishing crew don't even notice. And so I think as it becomes familiar, I suspect prices will drop because that fear factor doesn't have to be budgeted into the projects. There is a premium. It does cost us more up front, but it's worth it buying a better product at the end of the day. You know, and it's like any decision we make at home. Do you want to buy a cheap and nasty second-hand car and spend a fortune in maintaining it, or do you want to buy something with a better maintenance record and not have to maintain it over time? Now, when you know, all of the calculations we did not include life cycle cost to the user. This is just the costs to the DOT. And so, yeah, the other one that we could build into these, no one's doing it just yet, but I'm trying to figure out, find someone who can, is life cycle safety. You know, if you have to shut a bridge down to do maintenance on it every 5 years or every 40 years, how many lives is that going to save? Because every time you shut down a lane anywhere, traffic accidents increase. So if we can keep those out of the way, I think there's a huge benefit here. The initiative, I think, has to come from the agency. Because of this life cycle issue, is that expecting a contractor to put in a higher bid to provide a material that's more expensive, he's not going to get the job. If he's competing, he's coming in on a low bid. So therefore, I believe that it's critical that the agency has to write the language that says, we want it. Then everybody is bidding on the same playing field. And then I think we will find that the costs become manageable pretty quickly as everybody becomes familiar with the process of working with this material. All right, specifications. Since we started this contract, the CP Tech Center has actually published a guide specification for internally cured concrete. It was written predominantly by Jason Weiss, and it provides some language about how do you know that you're getting a good material? How much do you put into it? What sort of quality control procedures do you have to know that it's working in the mixture that you have? How do you design a mixture with internal curing aggregate in it? But the ground rules are actually remarkably simple. The lightweight material has to have about a 15% absorption. I didn't write on the slide, but you want it to give about 90% of that water back out at a relatively high relative humidity. You don't want to suck the water in and hold it, because then it becomes a decracker. You have to ensure that the material is wet when it goes in the mixture. You do need to keep an eye on that moisture state so that you can control your mixture proportions. You monitor the strength and formation factor of your mixture. In the lab afterwards, you'll have a pretty good handle on this is good stuff or this is not. Formation factor is not a term I've used before in this presentation, but it's basically a fairly simple calculation from the resistivity measure that I talked about earlier. This document is available on our website. If anybody needs any help getting it, email me and I will get it to you. So again, I can work with the DOT. You know, we provided some language, and if you need any help, we can help put together a spec that'll work within your system. I would suggest you write up some special provisions to encourage, better still require internal curing. And again, we can help with proportioning guidelines as needed. And that's what I have to say. I have to acknowledge, to my eyes, I think it was a pretty successful project. It was a lot of fun, not least of which due to the relationship with Tim Sturgis and Dan Miller and the help from Jill Martindale, our associate at Ohio University, who helped with local contacts, local materials, and when we did the field testing, they were invaluable in getting materials back to their lab and doing all of that work. And then from Iowa State, Caitlin Friesman and Brent Farris from my bridge group. I'm the materials geek, they were the bridge geeks, and a selection of students from both universities that helped us with actually getting the work done, getting the results out. And with that, that's what I have to say. What I would suggest, perhaps, if Tim or Dan is online, if they have any thoughts on how we can move the implementation side along from the DOT side. Otherwise, open it up for questions.
All right, Peter, can you hear us? It's Jill.
Yes, Jill, I can hear you.
Okay, so we've got a room full of people, and I guess we're going to ask them to talk really loud so Peter can hear and then answer. It's just here. It's off the computer.
It's a little fuzzy.
Is that better for you, Peter?
Yeah, that's great.
Okay. I guess for me, implementation going forward will be me speaking with district folks, central office folks on where we can go with plan notes and developing and locating structures probably in more prevalent areas that are more populated. So that would be our Cleveland area here, Toledo, Cincinnati, Akron, those sorts of places, and determine where we can find twin structures. Probably continue this with twin structures, do one with our standard mix, one with the internally cured mix, and specify accordingly, and then work with contractors, ready mix suppliers, and our Ohio concrete industry folks to get everything out there and help to educate folks and work with them as we can. The DiGeronimo Aggregates apparently has shut down. I haven't really talked with them or anything, but that seems to be the case. There is another source, and I'm not sure their absorption if it's high enough or not, but out of Gold Hill, North Carolina, there's a source that comes in through Cincinnati that we get via rail. So that may be another source that we have available for the lightweight aggregate. I think this is a great material that I think we can use. I know back in 2007, I'm actually looking at Eric Mack, who was also on the research project through Norb DeLotte. He was part of that research, and I was actually part of that research as well, just helping out on the side back in 2007, which was a report that you all used as well. So that's basically all I have. I'm behind this 100%, and I'm willing to draft the spec and kind of let you take a look at it, Peter, and get input from anybody that's out there. Ohio Concrete folks, ready mix suppliers. So I believe Rockport, you all supplied it. If you're here today, if you guys have anything to say about it, if you guys want to come up and speak up, you can, and we can kind of go from there. You want to come on up? Well, for everybody to hear. So yeah.
And Tim Keller's on here too. So we have participants all over, not just in this room.
Hello, Peter.
Hi.
Hi, this is Don Nichols. I'm wondering, you said the flexural strengths were lower. Were there 7-day breaks done on test cylinders?
I'm pretty sure there were.
Is this an issue because slag tends to build strength at a slower rate? So there's no alarms.
No, we've got flexural at 7-day. The tensile was actually higher for the field samples.
That didn't correlate with the beams that you broke, though.
Yeah, the lab tests were a little different. So again, but that we were dealing with slightly different materials. But for the decks that we actually built, the internally cured flexural tests were higher. Or split tensiles at any rate.
I just wondered if you correlated them.
Yeah, I hadn't tried to tie back. Because again, a big difference is that we're comparing apples and eggs, is that the lab work, yeah, I need to go back and chew on that a little bit. Good question.
Okay, thank you.
Anybody else? I know it's intimidating to come to the front of the room, but. Okay.
All right. So one of the items, or one of the elements for the project was we did have for the internal curing deck a maximum slump of 5. Now there is several reasons for that. We actually wanted it to be lower, but did kind of concede that there's not a lot of experience with pumping concrete at really low slumps in this area anymore. So the reason for that really has to do with depression cracking over the top mat of the rebar. So there's a good purpose for that. During the construction from the contractor, that's probably the element that we heard the most complaints about was the 5-inch slump max. But as far as pumping it came through okay. We didn't hear any complaints from the finishers. We heard complaints over the additional slump tests they had to do because they were losing quite a bit of slump through the pump. So they were trying to, come back and make sure that was within the range on the back side of the pump. So, and trying to get that dialed in on the front side. So there was quite a few additional slump tests that they were complaining about. But other than that, I didn't hear anything from any of the finishers that were complaining. Peter alluded to it in his presentation that, sometimes they don't even know that it's different. In this case, I think it was well communicated to everyone on the site that this one was a little bit different. But, we were kind of, we saw this Wilson Mills project coming up and we started looking at some of the MOT, noticed that, both decks were going to be poured relatively at the exact same time. So kind of figured this was a perfect project to do this kind of comparison on since we were eliminating so many variables environmentally and then also traffic wise and whatnot. So I'm pretty pleased with the way it came out. I was out there when they did the crack survey and saw exactly what Peter reported here, that you really couldn't find any on the internally cured deck. So I'm pretty happy with that. Just as a side note, there's been a lot of research on the early age cracking of the decks. And Peter, correct me if I'm wrong or misstating it here, but from what I remember in the literature reviews was that, if you can control your early age cracking within the first 3 years of the bridge deck, you're really setting up that baseline for the curve moving forward, which I believe was taken into account in your life cycle cost analysis, Peter.
Correct.
So.
Yeah.
Okay.
In fact, no, the life cycle did not include the effect of cracking. So it's even better.
Okay, so even better. Obviously you eliminate the cracks, you eliminate the potholes, you eliminate pathways to the steel. So you have a much better product in that end. So we're pretty, I'll be around long enough to at least see to the point where we would otherwise be probably overlaying the southbound deck. So I guess we'll see, in 10 years, really, 10, 15 years, this is, the promising thing that we're seeing now. But my understanding is, based on the data, we don't want to wait that long to verify it. We're going to start moving forward with some additional decks. And so I think this is something that's common for the contracting industry. I'm not going to want to move from that 5-inch slump, so I guess get used to that too. Yeah, that's really all I wanted to say on that. Yeah. So the question was whether or not the mix was used in the parapets. Yes, on the deck, not in the approach slabs. One other thing to note on this contract, we did include as part of the addendum that added this note in there, we did include an item for the shrinkage reducing admixtures. When we took a look at that and based on the lab data that we had, based on the cost of it, there were some other factors that were being introduced there that might be problematic. So we did decide to non-perform that and not use the shrinkage reducing admixtures for a number of reasons. One, cost. I think it was about, what was it, $30 a yard or something like that, $25 a yard. So, over the life of, the grand scale that we're thinking of here, that's a pretty significant cost, cubic yardage wise over, all of ODOT's program. So, that and there were some detrimental effects of the shrinkage reducing admixture that we saw in the test results that we really just wanted to see without that if we could still get the results we were looking for, and it appears good. Yeah, so part of the research shows that when you have the higher slumps, you end up with a depression area above the top mat of rebar. So by introducing that, you have a thinner section over top of the rebar, which is where that ends up cracking. So if you go out and look at a lot of the higher slump, and that's fairly, the grand scheme, that's a fairly new practice to be using the higher slump. I guess in the last couple of decades, but in that sense, the higher slump has introduced a lot of the early age cracking that we do see in the decks. So keeping that baseline lower at the early age, again, sets your curve for the total amount of cracks that you'll get over the life of the deck. So that lower slump helps out a lot. I know Kansas actually limits it to 3.5. And yes, they are able to pump that. I know there's a lot of concern with that, but feedback from Kansas has said that they don't have any issues with that now that the contractors have adapted and have gotten used to that. It's definitely a culture shock right off the bat, but they have gotten used to that and made the adjustments to make it work. Yes. Point of placement slump, yeah. Dan, I don't know if you want to speak to the air content. I thought we were going up with that anyhow. Aren't we? Yeah. Oh, okay. Yeah. Yeah, there's obvious workability issues that are going to have to make adjustments for that too. Your hose man's going to have to be a lot more accurate with that. And you might have a little bit of additional vibration, but it's going to have to be a learned thing that you deal with. Other questions?
Online.
None online. Okay.
So if there's no more questions, which I'm looking at, doesn't appear to be, this report is not quite finished yet, correct, Peter? We have
Correct.
some changes from Tim and Dan that need to be incorporated. When it is done, it will be published on the ODOT research website. You'll be able to go out and get the report as well as a small fact sheet, which gives a macro level look at this project. So if you want to dive into it, I know that academics like Peter always love it when people read their report, right, Peter?
Oh, yeah.
So I guess with that, we'll let you have your cold. Hopefully you get better and get over it.
Thank you very much.
We appreciate your time. Everybody online, we are done. This concludes our presentation. Thank you.
And again, thanks again for letting me do this remotely.